Welcome back to the Foundry by Forge College. Today, we're diving into programmatic transaction building and inspection. Now, this builds directly on our last lesson where we covered creating key pairs and sending manual transfers. But today, we're officially taking the training wheels off. In this explainer, we are transitioning away from typing out manual CLI commands and moving straight into fully automating your Solana transactions using code. So get ready, because we're about to upgrade you from a manual data entry clerk into a full-fledged Web3 transaction engineer. Let's get into it.
Here is the engineering schematic we're going to be following today. We're going to hit the transaction blueprint, assemble our components, sign on the dotted line, submit everything, inspect our diagnostics, and finally wrap it all up. All right, starting with Section 1, the transaction blueprint, moving from the CLI to code.
Now, you remember those manual CLI transfers you did previously, right? Well, doing that by hand is fantastic for learning the absolute fundamentals, but let's be real, it's terrible for scaling. You can't build an app that way. Today, we're going to automate those exact same steps. So what exactly are we building here? Well, think of a transaction as a highly secure shipping container. Inside this container, you bundle together your instructions, a recent block hash timestamp, a fee pair, and your cryptographic signatures. The Solana network actually needs all of these packed perfectly inside this container to process an action and effectively change the state of the network.
Okay, let's dive into Section 2, assembling the components. This is our parts list.
Every good machine starts with a solid parts list, and programmatic transactions are no different. When we assemble a transaction object using SolanaKit primitives, it's essentially a three-step assembly line. Step 1, you fetch a recent block hash. Step 2, you add your instruction objects. And Step 3, you set the fee pair's public key. Let's look a little bit closer at these parts on the line. First up, the recent block hash. Why do we even need this? Well, by calling getLatestBlockHash, we validate the absolute freshness of our package. Think of it kind of like a very strict expiration date on a carton of milk. It literally tells the network, hey, this transaction is brand new, it's not a duplicate, and no, you cannot replay it later to try and steal my funds. It's absolutely crucial for security.
Next up on the line are the instructions. Now, an instruction is a technical object that includes a program ID, the account metas, which basically just declare who is reading, writing, or signing, and a byte array payload. But to make that a bit simpler, if the overall transaction container is a sealed envelope, the instructions are the actual written letters you put inside it. A system program.transfer is a perfect example of this. It's an instruction representing a real state change. It's literally like a letter explicitly telling the network to move funds from one specific place to another inside our assembled package.
Moving right along to Section 3, signing the dotted line, our cryptographic approvals.
This is basically the managerial sign-off phase of our transaction. Just like those tedious corporate expense reports, your transaction isn't going anywhere without the proper signatures. Without these cryptographic approvals, your beautifully engineered package just gets thrown right in the trash. Now, there are two main ways we handle these approvals. On the one hand, we have single signer scenarios using tx.sign. This is super straightforward, just your fee payer signing off. But on the other hand, we have multiple signers using tx.partialSign, and this is incredibly useful for distributed workflows. Think of a situation where, say, a multi-sig authority and a payer both need to approve a transaction, but their keys live on completely different servers. Partial signing is what makes that kind of distributed security totally possible.
So once all those signatures are gathered up, we call transaction.serialize. This is a fun one. It takes our fully signed, somewhat bulky JavaScript object and squishes it down, like in a digital hydraulic press, into raw, network-readable bytes. It is exactly the equivalent of taping up the box, slapping a shipping label on it, and kicking it out the door.
Which brings us to Section 4, submission and confirmation, shipping the package.
It's time to actually ship those raw bytes to the network using sendRawTransaction and then track its delivery status. The crucial thing here is understanding how the network reports that delivery. We have 3 confirmation levels, and you can think of these exactly like shipping speeds for a physical package. First up, we have processed. This just means the node accepted it. It's super fast, great for quick UI feedback, kind of like getting a notification that your package was dropped off at the post office. Second, we have confirmed. This means a supermajority of validators have actually seen it. This is the sweet spot for most Web3 applications. It's like getting a tracking update that your package is out for delivery. And third, finalized. This is ultimate high-assurance finality. You want to use this for critical on-chain accounting where rollbacks are absolutely unacceptable. This is like your package being signed for, delivered, and locked securely inside a safe.
All right, Section 5, inspecting the diagnostics. Let's read those RPC logs.
because once we ship the transaction and get a confirmation, we need to know exactly what happened under the hood, right? To check our diagnostics, we fetch the transaction using its signature via getTransaction. This returns diagnostic data that is literally pure gold for developers. It lets us view the pre-balances and post-balances so we can mathematically prove that our funds actually moved exactly as intended, and even more importantly, we can inspect meta.log messages to see the exact output emitted by the program.
For example, inside those logs, you might see a textual readout that looks something like program log payout recorded ID equals 42. Parsing these logs is absolutely essential. It is exactly how you debug failures and correlate your off-chain databases with the actual on-chain realities. Seeing that ID equals 42 confirms exactly which record was updated.
And hey, like any good engineer, you've got to verify your work. Always cross-check your programmatic signature using Solana Confirm or Solana Transaction Get right in the CLI. This just double-checks that your code is actually doing what you intended to do on the live network.
Finally, Section 6, wrapping up, our final blueprint review.
We've covered a ton of ground today. Let's do a really quick recap of the entire life cycle. Step 1, you build the components. Step 2, you sign and serialize the package. Step 3, you submit it to the RPC and confirm delivery. And Step 4, you fetch and inspect those logs. You now have the exact blueprint you need to confidently automate your Solana interactions.
But real quick, before you go out there and start building, I have to give you a massive security warning. Never ever commit secret keys to your source files. Look, it's super easy to use local key pair files for quick testing, but in production, you absolutely must plan for secure key handling. In fact, minimizing private key exposure is exactly what we're going to be tackling in our very next lesson.
So I'm going to leave you with this final thought. If you can automate a simple transfer today, what complex, multi-instruction program are you going to build tomorrow? The possibilities here are literally endless. Thank you so much for joining me on this explainer. If you want to practice and troubleshoot these exact workflows with other developers, or just learn more about this subject and explore other deeply technical Web3 topics, head over to forge.college. Keep building, stay curious, and I'll see you in the next one.